Okay, YouTube, this is my first in a series of videos that I'm doing on polynomial functions and their graphs, in which we're going to kind of introduce what polynomial functions are and talk a little bit about the characteristics of their graphs as we lead into n behavior first. So let's take a look at the definition of a polynomial function. We say letting n be a non-negative integer and letting a subscript n minus 1, all the way down to a2, a1, a0. Let these be real numbers with the leading one there, a sub n. This cannot be equal to 0, but we say the function defined by this right here. So we say y equals, or f of x equals, a subscript n times x to the nth power plus a subscript n minus 1 times x to the n minus 1 plus all the way down to, and you'll notice here that the scheme is basically that the subscript and the exponent decrease together here, a to the, a subscript 1, x to the 1, plus a subscript 0. Kind of, we could write x to the 0 here if we cared to do it. This would be a polynomial function, and we say that this is a polynomial function of degree n. So a few things we want to write here. When we talk about polynomial functions, we're going to refer to the degree of the polynomial function as being the highest exponent on any of these terms here. And we say the number a sub n, this is the coefficient here, that is the coefficient of the dominant term. So we're going to refer to this as the leading coefficient. Okay, and you'll notice that when we have our polynomial function in this form where we have our highest exponent in the front and then they kind of go in descending order, what we're going to do is we're going to refer to this as standard form of a polynomial function. And standard form essentially means that exponents are going to go in descending order when we write these polynomial functions, but exponents descending if it's in standard form there. Nice thing about standard form is that it brings in order to things, but it also helps you see the degree and leading coefficient very, very, very easily, okay? But we say polynomial functions are these things where we say all of our coefficients are just real numbers, okay? Remember that they're real numbers, which means they just, there will be no imaginaries. And then we say that the degree here, we say n is non-negative, and it's not, it's a number usually, well, it's not negative, and it's an integer, okay? Let's put it that way. So all of your exponents here are non-negative integers. So when we talk about polynomial functions, I give an example of a couple here that are polynomials, and then we say a couple that are not polynomials. We say what makes it a polynomial? Basically, you're adding together a bunch of terms where you're multiplying by some variables to certain powers, and that's it. But it's just that your powers have to be non-negative. So you'll notice that your powers here are 5, 2, and technically x to the 0, that's a non-negative thing. Likewise, we say, looking at the coefficients are all real numbers. That is, I don't have any imaginaries sitting out there. So this must be a polynomial function if I'm adding up a bunch of terms with variables to certain powers that are non-negative, that are whole numbers. Okay. Looking at g of x, the interesting thing about this is it's in a factored form. So we have this negative 3x to the fourth being taken times x minus 2 being taken times x plus 3. But when you FOIL all this out, you FOIL this here, you get x squared plus x minus 6. And then you distribute your negative 3x to the fourth through, you get this final polynomial, the sixth degree polynomial here. But basically, you can see that this is also a polynomial here, even though it was written in factored form. Okay, so we would say yes, this would have a degree of 6, and the leading coefficient here would be negative 3. Now, things that are not polynomials would be things like this. We would say negative 3, the square root of x. And the reason why the square root of x is because when you rewrite it as x to the 1/2 power, which means the same thing as the square root of x, you have an exponent that is not a whole number here. And likewise, when we have an expression like this here, we say negative 3 over x squared plus root 2x squared plus 5. These two terms, technically, I gotta tell you, are fine. There's no imaginaries out in front as coefficients. You have non-negative exponents that aren't decimally. But when you look at this here, we'd say that's the same thing as negative 3 times x to the negative 2 if you move this base back up top. So because this would be a negative exponent, this would be non-polynomial function. So here's what I want to do. I actually, if I were to like open this Desmos here, I put these in earlier. I say here's our two polynomial functions. I just want to take a look at them. These are polynomial functions here, the same two we just talked about. Here's the first one, this little curvy polynomial function. Let me click that off and we'll click on the second one. You see that this is also, if I zoom out here just a little bit, kind of goes up and then down and then up and then down again and decreases forever and ever after that. Now when you look at these other two, this is a non-polynomial function. You can see that it kind of just starts here where x is 0 and goes to the right, and that's kind of an odd looking thing. And then when you look at this next one here, we say, ooh, okay, it looks like it gets really close to where x equals 0, but that it never gets to where x equals 0. There's like a break in the graph. So one significant thing about polynomials is their graphs are all very similar. Okay, so we're going to talk about what their graphs look like compared to non-polynomial functions. But we would say that a constant function, okay, when we give these polynomial functions a name depending upon their degree, but we say a constant function is f of x equals c where c is not 0. And we say this is some polynomial function with degree 0. We say a linear function is y equals mx plus b where m is not equal to 0. And we say that the polynomial function is of degree 1 since the highest exponent is 1 on any x value. Excuse me. And then a quadratic function, this is our y equals ax squared plus bx plus c where a is not 0. We say it's a polynomial function 2 of degree 2. We could say the highest exponent is 2, so its degree is 2. But basically, these are things we've seen before. So when you look at this table over here, it says here's the degree of your polynomial, the highest exponent. And as you increase, you see the names change here. We have our constant function. We might write a note here that this is a horizontal line. Horizontal line is a polynomial function. Okay, when we say this right here, we might as well write y equals mx plus b. This is a non-horizontal line here, a non-vertical line, but we call this as a linear first degree thing. And then quadratic things, remember, these are parabolas, so they either look like a u that opens upward or a u that opens downward. We're very familiar with those. But basically, we're going to extend this to now things that are third degree, fourth degree, higher degrees than 3. So they're going to get a little bit more complex. We want to be able to describe them in general. So really quickly, other than the constant, linear, and quadratic, third degree things we'll refer to as being cubic things for reasonable purposes. And then, quartic would be a fourth degree thing. So when we look at their graphs, one thing is certainly true about all polynomial functions. If you have a bunch of terms being added together in the fashion that we've seen in this previous page for being a polynomial, then we say that you get a smooth curve. And what we mean by smooth, let's just read this here. It says by smooth we mean that the graphs contain only rounded curves with no sharp corners. So an absolute value graph would not be a polynomial just because it has a sharp corner on it. Just as these are polynomial functions because they're very curvy. We saw that happen when we graphed those other two polynomials. We also say that they're continuous. And what we mean by continuous is that there are no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So one thing is very sure about all polynomial functions, you might as well write it right now, but is that the domain's always going to be all real numbers, okay? And you'll never have to lift your pencil off the page. So you see these really smooth, curvy things that are always continuous. And about the only other thing we notice here is that the end behavior here, they either keep increasing on the ends or keep decreasing on the ends, but they're doing one or the other on the ends here. So non-polynomial graphs, these would be examples of non-polynomial graphs right here. And just because of this bold face words up here, we can say, are they smooth or are they continuous? This first graph right here is discontinuous. It has a discontinuity right here. And so your pencil basically had to be lifted off the page. And then this right here, it's just, we have a sharp corner or a series of sharp corners, so that would disqualify it from being a polynomial function. So as we kind of explore polynomial functions, just know that they have a certain form, standard form that we like to write them in. Their domains are all real numbers as well as their graphs being smooth and continuous everywhere. Their end behaviors either go up or down on the ends, and they will neither be discontinuous nor have sharp turns. Cheers.